It's a great pleasure to have Tim Kovachy here to talk to us about his exciting work on matter wave interferometry. So Tim did a PhD and postdoc in Stanford University, working with Mark Kasovich there on interferometry, and now he's setting up with rubidium atoms, and now he's working on a brand new project on strontium, which he's going to tell us about. He's assistant professor at the Northwestern, in particular at the Northwestern Center for Fundamental Physics at Low Energy, and he's going to talk to us about the experiments that he's doing there, and I'll just leave him to tell us about it. Okay, and I'll keep an eye on the chat, and if there are any questions, put them in there, and we'll either activate you or read them out. Okay.
All right, thank you, Chris, for the introduction, and thanks for the invitation to give the colloquium today. Really excited to join you all. Is my screen showing up all right for everybody?
Yeah.
All right. So today I'll focus on talking about the MAGIS-100 100-meter tall atom interferometer that I, along with many collaborators, are in the process of building at Fermilab. For a summary of what I'll be discussing today, I'll begin with a brief overview of atom interferometry. I'll then talk about enabling technology advances for large area and long baseline atom interferometry that have been demonstrated with 10-meter baselines that really paved the way for MAGIS-100 and related experiments. And then I'll spend some time talking about the science motivation for going to these longer 100-meter and beyond baseline atom interferometers.
And it's I don't know. I've just lost track of time, so it definitely does not feel like.
Sorry, can people mute? Sorry.
Oh, and then finally, I'll spend some time talking about the specifics of the MAGIS-100 detector. In particular, a conceptual overview of how it gains its sensitivity to gravitational wave and dark matter signals, a brief summary of the experiment, and then a perspective for the future. And so atom interferometry, at least at a conceptual level, is quite similar to what may be more familiar in terms of optical interferometry. We take an atom's quantum mechanical wave function, which is often referred to as a matter wave, apply a beam splitter interaction to split this into two trajectories. Midway through, apply a mirror interaction to redirect the two trajectories toward each other. And then finally, the two trajectories interfere on a beam splitter, and we can observe an interference pattern and read out a phase. And a natural question that arises is, how does one actually make a beam splitter or a mirror for an atomic matter wave? We refer to these elements as atom optics. And there are several ways in which one can do this, but the method we use in the experiments I'll be talking about today is something called light pulse atom interferometry, in which we use laser pulses to transfer momentum to the atoms in order to manipulate their motional states. And so to see how this works, we can consider an atom that's initially in a ground internal state, and then we shine a laser beam on it. And if the laser beam is close enough to resonance, the atom can then absorb a photon to jump up to the excited internal state. But by conservation of momentum, it will also absorb the photon's momentum, which is equal to h bar k, where k is the wave number of the laser beam. And so the atom will then receive a momentum recoil and an associated velocity recoil equal to h bar k divided by the mass of the atom. Similarly, if the atom's already in its excited internal state and it undergoes stimulated emission of a photon into an existing laser beam, the atom will recoil in the direction opposite to the emitted photon. So that's how we can exchange momentum between the laser field and the atom. As for how this can actually make a beam splitter or a mirror, if one goes through and solves the dynamical quantum mechanical equations, you can find that if the atom is initially in the ground state and with some initial momentum p, if we leave the light pulse on for just the right amount of time, something that's often referred to as a pi/2 pulse, the atom is in a 50-50 superposition of either remaining in its initial state or absorbing a photon and being transferred to the excited internal state and receiving a momentum kick h bar k. And so this 50-50 superposition acts as a beam splitter operation. If we then leave the pulse on for twice as long, often referred to as a pi pulse, then the state absorbs the photon with close to 100% probability corresponding to a mirror or a reflection interaction. And so by tuning the pulse durations, we can tune between beam splitters and mirrors. And in an atom interferometer, what we ultimately measure is the phase difference between the two paths when we look at the interference pattern on the output ports. And the reason atom interferometers are useful for many different sorts of measurements is that this phase difference can be sensitive to a number of different physical signals of interest. These include, for example, accelerations such as gravitational accelerations, or in some cases, which will be relevant to the work discussed today, time variations of atomic energy levels. And generally speaking, the sensitivity of the atom interferometer phase to signals of interest will often increase both as we change the spatial distance between the two branches of the wave function, which I'll refer to as the wave function delocalization, and also the sensitivity will increase as we increase the total interferometer duration, increase the coherence time. So there's significant motivation to increasing both this delocalization and the coherence time. And so now, having given this brief overview of atom interferometry, I want to spend some time talking about recent technological advances that have really laid the groundwork for what we're planning to do in MAGIS-100. And one of these important advances, tying into the point I just made on the previous slide, was the realization of macroscopic scale atom interferometers, in which the wave function delocalization is pushed to truly macroscopic distances on the order of multiple tens of centimeters, and also where the time scale is pushed to long durations on the order of a couple of seconds. And we were able to achieve these large wave packet delocalizations by applying advanced beam splitter sequences, where instead of one pulse, we actually apply sequences of many pulses, up to 90 pulses, to separate the two branches of the interferometer by many photon recoils of momentum, so that the two branches separate out from each other more quickly. And in these interferometers, the sensitivity really gets quite large, for instance, to gravitational signals. And a number I like to mention as an example to illustrate this large intrinsic sensitivity is the Earth's gravity gradient. The fact that the gravitational acceleration due to the Earth changes slightly as you change your height. That's normally something we think of as quite a small effect. But in these atom interferometers, this effect of Earth's gravity gradient created actually a full 1 radian phase shift over just the small millimeter vertical size of the atom cloud, which is something we were able to clearly resolve. Another important technological development was the realization of these macroscopic scale interferometers in something that we refer to as a radiometer configuration, which is where we have 2 of these atom interferometers separated over a spatial baseline, and then we make a differential measurement between the 2 interferometers. And as we'll discuss later, this sort of gradiometer configuration lies at the heart of what we'll be doing in the MAGIS instrument. And it's especially important because in this differential measurement, a number of sources of noise cancel out as a common mode. Importantly, laser phase noise being one of them. And we are able to successfully demonstrate this common mode noise cancellation with these large-scale interferometers. To benchmark the sensitivity of this gravity gradiometer setup, what we did was bring in a test mass and then measure the gravitationally induced phase shift from this test mass. And we were able to measure, as we moved the test mass in and out, a reproducible 1 radian phase shift, which was consistent with our theoretical expectations. And we also measured the response of the atom interferometer to the test mass as a function of how high we launched the atoms, which was also consistent with our theoretical expectations. And one interesting science result that emerged from this work was the first observation of a phase shift in a matter wave interferometer arising from space-time curvature across the wave function of a single delocalized particle. And the physical significance of this comes from the perspective that from a general relativistic point of view, gravity in a coordinate invariant sense is in many ways defined by its curvature, or in other words, by the tidal forces that it induces. Because in contrast to local accelerations, curvature or tidal forces represent a gravitational effect that cannot be boosted away by making a coordinate transformation. And so for this reason, such curvature-induced phase shifts, if they could be observed, had been described in the literature for a number of decades as being the first true manifestation of gravitation in a quantum system. And in this situation, the wave function can no longer be said to exist in a single local inertial frame and experiences gravity non-locally. However, although people had wanted to observe this effect for a number of decades, it was only recently that the wave function delocalization got large enough that there were resolvable gravitational tidal forces across it. But what we were able to observe in these interferometers was a curvature or tidal force induced phase shift from our source mass across the wave function due to these lead brick source masses. And in addition to seeing gravity affect a quantum system in this new regime, some theorists had subsequently analyzed our results and showed that they placed bounds on certain gravitational decoherence models. And so the work that I just mentioned was carried out with rubidium atoms in a 10-meter atomic fountain in the Kovachy lab at Stanford, where, as Chris mentioned, I did my PhD and postdoc work. And in many ways, this 10-meter fountain developed a lot of the key technologies and paved the way for MAGIS-100. How this works is that at the bottom of the fountain, we prepare our ultra-cold atoms. We then use optical forces arising from an optical lattice to vertically launch the atoms on a ballistic free fall trajectory. And as the atoms are freely falling over several seconds, we can perform long duration atom interferometry. And one of the many lessons we learned from this apparatus, which was pushing the limits of interferometer sensitivity, is that there are certain effects that as you go to larger scale atom interferometers that you have to pay attention to as you become more sensitive that weren't immediately noticeable in smaller scale apparatus. And one of these was the fact that Coriolis forces due to Earth's rotation can actually cause significant phase shifts in these ultra-sensitive atom interferometers. And in fact, if we applied no compensation of these Coriolis-induced phase shifts, they would have entirely washed out our interference signal. And so what we did was we counter-rotated our laser beams against Earth's rotation to effectively compensate for these Coriolis forces. We did this counter-rotation using a mirror on a piezo tip tilt stage. And that compensation technique ended up working very well, and we plan to implement similar methods in MAGIS-100. Other important developments that paved the way for MAGIS-100 involve advances in cold atom techniques with strontium, because for reasons that I'll discuss later, MAGIS-100 will find it quite favorable to use strontium atoms instead of rubidium atoms. And fortunately, there have been some very substantial advances in cooling protocols for strontium atoms in recent years, to the extent that we're actually now procuring the cold strontium beam sources for MAGIS commercially, actually. And also there have been impressive advances in coherently interrogating what's called the clock transition of strontium, which is important for MAGIS-100. I'll say more about why that is later. But in both the optical atomic clock community and also in the atom interferometry community, there's been some excellent work on making use of this clock transition that we'll be building on. And the highly stable lasers that one wants for interrogating this transition can be procured commercially. And so now, having set the background in terms of enabling technological advances, the next piece of background I want to give before going into the MAGIS-100 detector itself is to go through some of our key science motivations. And one of these is to search for dark matter. There's quite a bit of compelling astrophysical evidence that dark matter makes up a significant portion of the energy budget of our universe, but still we don't know the exact nature of dark matter. And so a topic at the forefront of modern physics is to try to search for various well-motivated dark matter candidates to see if we can learn more about dark matter and how it may couple to ordinary matter. And one set of dark matter candidates that has emerged as being quite promising falls under the class of what's often referred to as ultralight wave-like dark matter. And this dark matter corresponds to bosonic fields, and it can be thought of as acting more like a coherent wave-like background as opposed to a set of individual discrete particles. And this wave-like dark matter can have various couplings to ordinary matter, which in precision experiments has the potential to lead to observable signals. As just one example of, for instance, a scalar dark matter field, this could couple, for instance, to electrons or to photons, and correspondingly lead to small oscillations in fundamental constants such as the electron mass or the fine structure constant at a frequency corresponding to the Compton frequency associated with the mass of the dark matter. And if these constants were to oscillate in time, atomic energy levels are affected by these constants. So one physical ramification that people can look for is that the energy spacing between atomic transitions would undergo slight oscillations due to the dark matter at this associated Compton frequency. And so one challenge in searching for this ultralight wave-like dark matter is a priori, we don't know, we have no, or at least no very definite theoretical constraints on what the mass and associated Compton frequency of the dark matter would be. So there's a large, many order of magnitude range of masses that one would have to search over in order to do a complete search for this sort of dark matter, which is certainly a daunting challenge. But fortunately, given the importance of trying our best to identify the nature of dark matter, there is a broad community of people who are really up to tackling this challenge and are applying a broad range of technologies to search over different regions of this mass spectrum with an aim to cover the whole mass range, which does require very different methods for different frequency ranges. And atom interferometers appear promising for approaching the lower end of this frequency range. And dark matter signatures that one could look for using atom interferometers such as MAGIS include the time-dependent atomic energy levels I mentioned on the previous slide. And another possible signature is oscillating composition dependent accelerations that would effectively look like equivalence principle violating accelerations that one can look for using dual isotope atom interferometers. Next, in addition to dark matter, another key science motivation is studying foundational quantum science. The long free-fall times that will be available in long baseline atom interferometers such as MAGIS offer the potential to further extend quantum coherence to distance scales even beyond the current state of the art, out to hopefully several meters for times of many seconds, and perhaps with future research and development in advanced atomic beam splitters, maybe even up to tens of meters in the future. So this would allow us to study quantum mechanics in really an unprecedented macroscopic regime, and also at the same time test a variety of proposed fundamental decoherence mechanisms, some of which are related to gravity, like the one I mentioned that we tested in our earlier work, which would put a constraint on fundamentally how large one could make a quantum superposition before these certain decoherence mechanisms start to limit you. And then finally, and very importantly, one of our key motivations is gravitational wave detection. And as we've seen with the recent LIGO and Virgo detections, gravitational waves are an incredibly exciting development for science as a whole. They act as an entirely new carrier for astronomy, generated by moving mass instead of moving electric charge, to allow us to study new types of sources. They offer the potential for probing the earliest times in the universe and studying the corresponding high energy scales, and also to study gravity in extreme strong field regimes, such as one would get in a black hole. And as we've seen, terrestrial laser interferometer detectors for gravitational waves have proven to be incredibly successful. And these detectors have their peak sensitivity above frequencies on the order of several hertz, because at lower frequencies for terrestrial detectors, they're significantly limited by seismic noise. At lower frequencies, with a planned peak sensitivity in the 1 millihertz to 100 millihertz regime, the planned LISA space mission set to launch in, I believe, the 2030s will offer some exciting expansions of the region of the gravitational wave spectrum that we can probe. And I should also mention that there are proposals to extend the LISA concept to higher frequencies. And so if one looks at the sensitivity curves of LIGO and LISA, one can see that between their respective peak sensitivities, there's something of a gap in what we call the mid-band frequency range between about 0.1 hertz and 10 hertz. And what's exciting is that we think this is a frequency range where atomic gravitational wave detectors have the potential to make a valuable contribution. And I think there's really an exciting science case for exploring gravitational waves in the mid-band. And just to go through some of the reasons for why I feel this way. First, in general terms, historically, every time we've opened up a new frequency band or modality of astrophysical detection, we've discovered something new and interesting. For example, when we've opened up different regions of the electromagnetic spectrum. And so we might expect the same to hold true for the gravitational wave spectrum. But beyond these general considerations, and more concretely, what one would definitely be able to do with a sufficiently sensitive mid-band detector would be to observe the sorts of sources we already know exist from LIGO when they're younger, when they're in this mid-band range and before they may transition into the LIGO frequency band. The mid-band also appears promising for searching for cosmological signals that could give insight into the high energy physics of the early universe. I won't talk through these all, but I've just listed several potentially interesting examples that could show up in the midband. And an advantage of the midband is that it's at low enough frequency that one could potentially have sensitivity to these signals, but also at high enough frequency that it avoids what's called white dwarf confusion noise, which is backgrounds in the gravitational wave signals arising from white dwarfs, which could potentially obscure any cosmological signals. Another exciting region to look in the midband is that it appears promising for sky localization of certain astrophysical sources. And because many binary sources that would later transition into the LIGO band in the last moments of their life could spend many months in the midband, these months would provide enough observation time to provide advanced sky localization and forewarning information to allow optical telescopes to repoint themselves in order to observe the run-up to the ultimate coalescence with electromagnetic telescopes, in addition to these gravitational wave observations, which would be very exciting from the perspective of multi-messenger astronomy. And finally, there are a number of interesting astrophysical sources which one could hope to study in the midband, including white dwarf binaries, which are related to type 1a supernovae, and also intermediate mass black holes. And LIGO's recent measurement of intermediate mass black holes make this especially timely. And just to say a bit more about the sky position determination and why the midband may be favorable for this, is that the angular resolution one can achieve improves both when one observes gravitational waves with a shorter wavelength or higher frequency, and also when one can make different measurements of your source separated over a longer spatial baseline. And advantageous features of the midband is that they still, in this range, we still maintain a relatively small wavelength in comparison to the sort of low millihertz frequencies, but also we're at a low enough frequency in the midband that many sources will have a long enough lifetime, on the order of months, that the Earth can substantially reorient itself around the sun due to its orbit around the sun, which will allow the Earth's natural orbit to give us a large baseline over which to make these measurements to determine the angular localization. And so now I want to get into talking about the MAGIS-100 detector that we're currently in the process of designing and building at Fermilab. And this detector will be built in an existing 100-meter tall underground access shaft at Fermilab, and it will be used to search for the dark matter couplings that I discussed, perform fundamental quantum science, and then also serve as a pathfinder experiment for midband gravitational wave detection that we hope will serve as an intermediate step to an ultimate full kilometer scale terrestrial detector that would have enough sensitivity to detect midband gravitational waves from known sources. And MAGIS-100, since it's a sizable experimental effort, it's important that we have many institutions making significant contributions to this effort, one of which is your own department at Oxford. And just to say a few words about activities at Oxford. Oxford is one of the key partners on MAGIS. 4 faculty involved in the collaboration: Daniela Bortoletto, Chris Foote, John March Russell, and Ian Shipsey. Also 2 postdocs at the moment. And key contributions that Oxford is working on include the development of low noise cameras for detecting the atom interference patterns, which is one of the most important subsystems for ensuring that the experiment reaches its goal in terms of a noise floor. Also, theory support. John March Russell has already been critical for helping us analyze what the science reach of the experiment could be. Coordination on design and procurement of the ultra high quality in vacuum optics we need for our very clean laser beams for the experiment, and also coordination on the technology research and development, such as advanced atom sources and high power lasers that will need to push the sensitivity to the level to hopefully ultimately detect gravitational waves. And another way in which Oxford is contributing to this effort is through being at the forefront of the AEON collaboration. And AEON is an exciting UK-based effort to form a partner instrument to MAGIS. And I like to think of this as being largely analogous to the LIGO-Virgo partnership, which has been so fruitful in the field of gravitational wave detection. And AEON 10, the 10-meter version of AEON, is being hosted at Oxford in the new state-of-the-art Beecroft Physics building, which will offer an ultra-low vibrational noise environment, which will certainly be valuable for helping the instrument reach optimal levels of performance. And one of the key areas in which AEON and MAGIS will be working together is to explore networking strategies, which will allow for both enhanced searches for dark matter and for gravitational waves. And I think this networking will be really critical for this technology to reach its full potential. And I've just listed here a number of Oxford AEON collaborators, including the MAGIS team, plus several additional researchers and project management team members. And then just to say what I hope the ultimate vision for this research program will be, is to have a global network of these long baseline atomic detectors. And in addition to MAGIS and the AEON detector that I just talked about, the construction of the MIGA detector in France is already underway, which will also use long baseline atom interferometry to search for gravitational waves using complementary methods as MAGIS and AEON. There's also the Zyga detector in China, and potentially other efforts may begin as well. There's also been some interesting recent proposals to use optical lattice atomic clocks in space for similar purposes. And there's actually quite a bit of conceptual similarity between the atom interferometry work and this atomic clock work to allow some synergistic technology developments. And so now I would like to spend a bit of time going through the concept of how MAGIS and AEON and related detectors actually gain their sensitivity to gravitational waves and to dark matter. And this concept relies on several essential features. First, it relies on the fact that light will propagate across a baseline at a constant speed in vacuum. And then it also makes use of the fact that atoms can be used to form both excellent clocks and also very good inertial proof masses. The latter point related to the fact that we'll have our atoms freely falling in vacuum and not mechanically connected to the Earth. And the basic concept of the measurement is that we'll have two atom interferometers which will configure to act effectively as clocks, separated over a baseline. I've shown the baseline horizontally here just for aspect ratio reasons, but in MAGIS this will actually be vertical. What we can do is send a light pulse over this baseline, and then the clocks on either end of the baseline will then measure the number of clock ticks associated by this light transit time over the baseline. And then a gravitational wave would change the number of measured clock times associated with this transit by actually modifying this light transit time. One can think of this in certain frames as the gravitational wave is essentially stretching the baseline and therefore changing the light transit time. Dark matter signals, on the other hand, would change the number of clock ticks associated with the transit over the baseline, not by changing the baseline length, but by changing the clock frequency, corresponding, in this case, to the atomic transition frequency. And then finally, we'll send many pulses across the baseline, which will correspond due to the fact I discussed earlier, that when we absorb or emit photons, there's momentum transfer to large momentum transfer in order to coherently enhance the signal. And we'll make use in this experiment of atom interferometry acting on the strontium clock transition that I mentioned earlier. And what's special about this transition is that it's very narrow and correspondingly has a very long-lived excited state with a natural lifetime in excess of 100 seconds. And at the same time, it has a frequency corresponding to visible light, a wavelength of 698 nanometers. So this transition allows one to have long-lived superpositions of ground and excited states with a large energy difference, which is useful for making very precise timing measurements. And is in fact why it's called the clock transition. It's used in some of the very best atomic clocks. And just to give a little bit more detailed conceptual picture of the measurement sequence, we have our two atomic clocks as before separated over the baseline. And when we send our first laser pulse across the baseline, when the laser pulse interacts with a given one of the atomic clocks, it performs a beam splitter operation to split the atom into a 50-50 superposition of the ground and excited states. Then after this initial initialization pulse, which we can think of as starting the clock ticking, we allow the atoms to freely fall for a time before finishing the sequence with the second pulse going across the baseline. And so during this free evolution time, due to the different energies of the internal states, we accrue a phase difference between the two parts of the wave function equal to the atomic transition frequency omega A times the free fall time capital T. And then when we finish the sequence by sending the second pulse across the baseline, when the second pulse interacts with each atom, it then interferes these two parts of the wave function, and we observe an interference pattern with a phase equal to this omega A times T factor. And what we can ask ourselves is, do we observe a differential phase signal between the two clocks separated over the baseline? And the answer is, in our zeroth order situation, no. Because although the clock on the left received its laser pulse first due to the finite light travel time over the baseline, so it started ticking earlier, it also received the second pulse first by the same amount, and so stopped ticking earlier as well by the same time, equal to the baseline length L divided by the speed of light c. So the total amount of time that both clocks spend ticking is actually equal, so we do not observe any differential phase shift. On the other hand, if there's a gravitational wave present, this will change the situation because the gravitational wave can effectively be thought of as causing an oscillating baseline length between the two clocks. And so therefore, the light travel time can change between the first pulse and the second pulse, causing the second atomic clock to either spend a little bit more or a little bit less time accumulating phase, proportional to the strain times the baseline length divided by the speed of light. And so a gravitational wave would manifest as actually inducing a differential phase shift between the two clocks. And we would then see this differential phase shift oscillate in time according to the time dependence of the gravitational wave. Now, one last piece of the puzzle that I should mention to give us a complete view of a conceptual picture of how the instrument works is that because our atoms are freely falling, they're not trapped so that they can act as very good inertial proof masses. As we discussed earlier in the talk, we have to account for the photon momentum recoil that the atoms receive when they transition between the ground and excited clock states. And so in addition to the internal state dynamics of the atom, we have to consider also the external center of mass motion of the atom due to these momentum recoils. So in addition to having an atomic clock where we have superpositions of different internal states, the different branches of the wave function also separate out spatially. And so we have to be sure to implement a multi-pulse sequence with an initial beam splitter, a mirror, and a final beam splitter as discussed earlier, so that the spatial trajectories of the two parts of the wave function overlap and can interfere. And for this reason, because we have dynamics both in the internal and external degrees of freedom, what we really have here is a hybrid of a clock and an atom interferometer. And such hybrid clock-atom interferometry has been demonstrated recently on the 698 nanometer transition of strontium, and large momentum transfer atom optics have been demonstrated on the 689 transition of strontium, which also serves effectively as a clock transition, just with a bit less of a lifetime, but with the same fundamental mechanism by our collaborator, Jason Hogan. And so in this full picture, the phase shift still arises from the same mechanism, from the finite light travel time. For instance, if we look at a given zone of the interferometer, for example, the first beam splitter, these squiggly lines corresponding to laser pulses, because they take a finite amount of time to cross the baseline, during this first beam splitter zone, the portion of the left interferometer that gets kicked, as opposed to the portion of the right interferometer that receives the kick. The left interferometer gets more time spent in the excited state by an amount corresponding to the light travel time L over C, and this leads the left interferometer to accumulate more phase equal to this atomic transition frequency times this extra light travel time. But when we consider the contributions to the differential phase between all three zones of the interferometer, in the absence of a gravitational wave or dark matter signal, these differences that each zones contribute to the differential phase shift between interferometers cancels out. However, if there's a gravitational wave present that leads to an oscillating baseline length between the different zones, the beam splitter 1, the mirror, and beam splitter 2, then that can make it so that the contributions from the different zones no longer cancel with each other, and we get a signal that we can measure. And similarly, in the case of dark matter, if omega A, the atomic transition frequency, oscillates, then that's another way by which we can get a signal that does not cancel between the different zones. And so just to say a bit more about the large momentum transfer sequence, what that corresponds to is we exchange many pulses across the baseline where we get additional sequences that the atom spends in the excited state, which is sensitive to the baseline length. And so since we then get n of these sequences corresponding proportionally to the number of pairs of pulses n exchanged across the baseline, the sensitivity of the instrument scales up proportionally with these number of extra pulses. And because of the transfer of momentum between the laser field and the atoms, these additional pulses also give us a larger momentum splitting between the two interferometer arms. One additional useful feature of atom interferometry that I should mention is that because we can, on the fly, change the geometry of the atom interferometer just by programming in a different pulse sequence, we can switch over to what's called a resonant detection sequence, where the interferometer consists of a series of multiple loops that the two different trajectories form. And this will give us a resonant response where we enhance our sensitivity to gravitational waves or a dark matter signal at the frequency of this looping, at the cost of bandwidth of the detection. And one can make a close analogy here to lock-in detection. And so these sorts of resonance sequences are something that we'll be able to explore with MAGIS-100. And one could imagine these being useful for search strategies where we would start off in a broadband search mode, identify an initial source and determine its frequency, and then zoom in with a resonance sequence on that particular frequency to look at the source more closely. And then finally, my last bit I want to say about the conceptual aspect of the experiment is that, as I mentioned earlier, this gradiometer configuration where we make a differential measurement between the two atom interferometers over a baseline is essential for canceling out sources of noise such as laser phase noise. And the issue with laser phase noise is that when an atom, for instance, absorbs a photon from a laser to transition part of its wave function from the ground to excited state, the phase of the laser beam gets imprinted on the atom's wave function as is shown here. And that can be a problem because then the noise of the laser gets read into noise in the atom interferometer. But because we do this differential measurement scheme where the same laser pulse with the same phase interacts with both atom interferometers, to a high degree, this phase noise is imprinted in a common way, and so cancels out in the differential measurement. And so I think I'll pause here. I just have, just before I go into the very last part of the talk, saying a few words about MAGIS-100 to see if there are any questions that have come up in the chat or Q&A along the way.
Okay, I can't see any questions in the chat at the moment. So if anybody spontaneously wants to unmute themselves and ask a question, they can.
Yeah, I would like to ask, if possible, if you can hear me okay.
Yeah, I can hear you.
Yeah, so I know you haven't spoken about this too much here, but I would like to ask you if you have an opinion when it comes to the imaging system, you know, getting the images once you fluoresce these atom clouds at the end. If you have an opinion on, as always with these things, there's trade-offs in terms of, you know, noise, quantum efficiency, spatial resolution. If you have an opinion on what parameters are of most importance for getting the kind of information you want from these images.
Yes, that's an excellent question, and in fact, a trade-off that I've had to contend with in some of my previous experiments. So basically, in terms of quantum efficiency and noise of the camera, if we can make those as good as technologically possible, that helps in a very significant way, because during the imaging process, there are two competing factors that we have to deal with. The first factor is that, well, if we can just apply fluorescence to the atom cloud for a longer amount of time so that we can collect more photons on the camera, that helps with the signal to noise ratio to overcome the electronic noise present in the camera. However, on the other hand, as we're fluorescing the atom cloud, that leads to the different atoms as they absorb and emit photons during the fluorescence process. The atom cloud will undergo spatial diffusion. And so then any spatial features on the interference pattern, for example, if you're looking at spatial fringes, will tend to get blurred out. And one can do integrated detection where you just count the number of atoms in each interferometer output port and don't look at the spatial features of the interference pattern. However, I found it very useful, and I suspect this will be very useful in MAGIS-100 to have a good spatial resolution on the interference pattern in order to resolve phase shifts that vary across the atom cloud. And I think this is going to be critical for characterizing certain sources of systematic errors, such as, for example, velocity-dependent phase shifts from residual Coriolis forces, or phase shifts from imperfections in the laser wavefront that will vary across the cloud. And so basically, to answer your question, to the extent possible, I'd like to have the best of both worlds, where we can overcome the electronic noise of the camera, have enough photons to do that, while at the same time imaging for short enough time so that we can minimize the blurring of the interference pattern. And what one can really do to help this, and ties into Oxford's effort, is the better you can make your camera, the lower the electronic noise and the higher your quantum efficiency, the fewer photons you need to scatter in order to overcome that electronic noise. And therefore, for being able to overcome your electronic noise, you can minimize the blurring of your interference pattern. Now, I should also mention that something I've applied in the past, and in which we're looking in. Oh, sorry.
I was just going to say, yeah, it's a very good answer, but I was just wondering whether we should carry on with the main thought.
Sorry, I will.
Because you might lose a bit of the audience after
Yes.
1 hour. I'm not sure.
Yeah. Okay. So I will carry on with the talk, but Daniel, I'd be more than happy to. This is a very interesting topic, so I'd be more than happy to discuss with you in more detail, either after the talk, or if you'd like to just talk over Zoom at some point, I'd be very happy to do so.
Okay, thank you very much.
Yeah, it's an excellent question. But yes, I will carry on with the talk. All right, so just to finish up, I just want to say a few words about the MAGIS-100 experiment. Here I've shown some design models of the experiment, and the vertical interferometer region will consist of 17 modules, which will contain magnetic shielding, regions of vacuum pipe, and current carrying wires for generating biased magnetic fields that the atoms need. In panel C here, that's an example of a single module. We'll then have 3 strontium atom sources over the baseline, each of which will have the capability to locally launch atoms. And then we'll be integrating in a high power laser system, which will be able to rapidly tune the frequency of, and we'll be implementing spatial filtering techniques to obtain a very clean laser beam mode. And also, as we did in the Stanford apparatus, use piezo tip tilt mirrors for finely controlled laser pointing. And construction and testing of these subsystems is underway. For flexibility, we'll be able to operate the detector in several different operation modes, some of which are illustrated here. In mode A, without launching the atoms, we can obtain a maximum drop time by dropping the atoms from the upper 2 sources. Alternatively, we can launch atoms from the lower source and the upper source to maximize the gradiometer baseline. In the 3rd mode, we can operate 3 simultaneous interferometers from all of the different atom sources, which will be useful for characterizing certain sources of noise that I'll mention later. And then finally, to search for certain dark matter couplings, we can implement dual isotope atom interferometers launched from a common source down at the bottom. Just to briefly mention, one of the main systems we're working on at Northwestern is we're currently building and testing the high power interferometry laser system. And an important aspect that we've paid a lot of attention to in our design and testing is that we need to maintain both a very high level of frequency stability and simultaneously a high level of tunability to address the different atoms at different velocities. And so this is something we've paid close attention to in the design. For actually delivering the laser beam, an important source of systematic errors can be that errors in the laser wavefront due to perturbations in the beam's spatial mode, such as the ripples shown in this animation, can lead to unwanted systematic effects. But fortunately, if a laser beam propagates in free space, to an extent, it will be self-cleaning, as illustrated in this animation, because the perturbations on the beam will tend to diffract out into side peaks. And so we've implemented our design a free spot propagation region, which will allow for this diffraction cleaning of the beam to ensure as nice and smooth of a beam spatial profile as possible. And then after this free space propagation in vacuum, we've sourced ultra high quality in vacuum optics to reduce any additional perturbations introduced by those optics on the beam. And our design of this beam delivery system has been guided both by analytical calculations and numerical simulations of the cleaning of the beam. I've just shown a couple quick examples here, where if we have an initial beam that has a perturbation, such as a small absorptive disk or an exaggerated intensity grading, after the free propagation, these perturbations nicely diffract out of the beam, leaving us with a very smooth Gaussian profile. And so finally, in just my last few slides, I'd like to comment on some of our goals for sensitivity for dark matter and gravitational wave searches. For the dark matter searches, I've shown here some goal search sensitivity curves, both for coupling to the electron mass and coupling to the fine structure constant, both for MAGIS-100 and for an anticipated kilometer scale detector in the future. And also the dual isotope mode will allow us to search for vector dark matter that couples, for instance, to the baryon minus lepton number. And the solid blue curve here shows an initial goal. The dashed curve shows goals for improvement after research and development efforts. And in all cases, we're hoping to be able to make significant improvements over the current state-of-the-art bounds. And finally, in terms of gravitational waves, the initial sensitivity goal for MAGIS-100 is the solid blue curve on the left, which corresponds to extending current state-of-the-art parameters to the 100-meter baseline. And then an important part of the MAGIS research program is to undergo a concerted research and development effort using MAGIS-100 as a platform to improve detector parameters and thereby improve the sensitivity. I'll briefly mention a bit more about that on the next slide. But what we hope to ultimately achieve if this technology development goes as planned in a kilometer scale detector is this green sensitivity curve on the right, which would be sensitive enough to detect known sources in the midband frequency range. And then further in the future, one could envision a space-based detector, which one could operate in either a broadband or a resonant mode. Now, one important aspect of these plots is these orange bands shown here, labeled GGN, which stand for an effect called Newtonian gravity gradient noise, which is quite an important effect for terrestrial detectors at lower frequencies. And what this corresponds to is that although to zeroth order, our atoms are decoupled from seismic noise because they're not mechanically connected to the Earth, seismic waves passing through can still disturb the local mass distribution, causing oscillating gravity gradients that can serve as a noise background. And these systematics will be important to characterize and contend with. Finally, just to mention briefly some of the research and development directions that we're pursuing, and we'll be collaborating with Aeon on these as well, is to try to boost the sensitivity by going to larger momentum transfer atom optics, going from the current state-of-the-art of on the order of 100 photon momentum kicks to hopefully up to on the order to 1,000 and then even up to 10,000 kicks. And an advantage that strontium has over rubidium for this case is that atom loss due to residual spontaneous emission from our atoms is multiple orders of magnitude lower for atom optics on the strontium clock transition than for atom optics using rubidium atoms. And residual atom loss due to spontaneous emission was one of our major limitations in our previous work for rubidium. So we hope that by reducing this, that will open up some promising possibilities. We're also actively exploring using quantum control protocols, optimal quantum control, borrowed from the quantum computation community to create pulses with better efficiency and reduced dephasing. In other words, higher fidelity pulses, to use some quantum computing language, which will be important for when we stack up the number of pulses to these very high numbers. And we've also left room to upgrade to even more laser power, which is beneficial if one wants to improve the efficiency of each pulse. Of course, as one improves the sensitivity, one also becomes more sensitive to various noise sources. So an important part of this research and development effort will be to improve our ability to mitigate these noise sources. An important one being the GGN I mentioned on the last slide. And a promising idea that was originated from the MEGA collaboration, in which we also hope to study, is that if one uses a string of multiple interferometers along the vertical baseline, as opposed to just an interferometer at the top and an interferometer at the bottom, one can map out the phase as a function of height. And whereas a gravitational wave or a dark matter signal would induce a phase that varies linearly with height, a GGN signal would nominally be expected to have an exponential dependence with height. And so we're interested in investigating the use of spatially resolved detection to try to distinguish the GGN noise background from the gravitational wave signal. And then finally, there are efforts to improve the phase resolution by developing higher flux atom sources and spin squeezing techniques for strontium atoms to make use of entanglement for better phase resolution. And so finally, to conclude, long baseline atom interferometry, I think, appears very promising for dark matter searches, gravitational wave detection, and foundational quantum science. The goal of MAGIS-100 is to serve as a pathfinder experiment in these areas and a test bed for advancing the relevant technologies. And we're excited that there are active efforts to develop a global network of such detectors and potentially future detectors in space. So I'd like to acknowledge the many people and research groups involved in this effort, and thank you for your attention.
Maybe I'll clap on behalf of everybody. Thanks very much indeed. Okay, well, it was very comprehensive and great talk about this fascinating work. So are there any questions? I can't see any have appeared in the chat yet. I guess it takes a bit of time sometimes for people to respond. Does anybody want to unmute and ask a question, or shall I? I mean, I have got one myself. So you talked about the GGN just at the end there, which obviously is a crucial factor, you know, and by using multiple interferometers, that's an advantage over, you know, which, for example, laser interferometers can't use. I mean, how far do you think that can be pushed to those lines you had of the limitations of GGN? How far across can those be pushed? Yeah,
I think that's really an excellent question, and one of the key questions that we'll have to address with these experiments in some theoretical modeling that we're currently working on, and this is being led by Jeremiah Mitchell, who was our first PhD student from MAGIS-100 and now is a Kavli Fellow at Cambridge with Val Gibson. He's doing some nice simulation work that suggests that in principle, one could hope to push this down by a couple orders of magnitude to allow us to, take this 10 to the minus 17 portion of the curve on the left and push it down to 10 to the minus 19 at this kind of this 0.3 Hertz range. So there's some optimism that it could be pushed down by an order of magnitude or two. But the qualifier I should give, and the things we need to understand better, is that his analysis has been assuming this ideal exponential fall off with height and studying statistically with that exponential fall off, how well could we discriminate this from the actual gravitational wave signal. But in order to really verify that, of course, we'll have to do it in the experiment, but even theoretically, some important next steps will be to include some complications, such as the fact that if the ground is non-uniform, just the density of rock or soil in the ground, that could affect the spatial profile of the seismic waves, or if there are stray reflections due to seismic waves, to cause the profile of the wave versus height to be a bit more complicated. And so how well we can actually understand that and model that out, I think is still a bit of an open question where we'll probably need to involve some geophysicists. So I think there's optimism for a couple of orders of magnitude, but there's some more due diligence that we'll need to do to really confirm that.
Okay, that's great. I see Richard.
Yes, hello. Yeah, thanks for the talk. You mentioned a bit about optimum control and perhaps composite pulses, and I was wondering how much you'd modeled which pulses you might use, and whether you were worried that it's quite difficult to generate enough pulse area on such a narrow line width transition to do LMT with constant pulses.
Yeah, both excellent questions. And so I think there's certainly been some previous work in atom interferometry just showing that both very basic composite pulses can help just your standard pi/2 pulse, pi pulse where you shift the phase by 90 degrees, and then pi/2 pulse, or more even more complex ones have helped, not on the clock transition yet, but just for basic Raman transitions, for instance, and even some work showing that more complex optimal quantum control waveforms experimentally and theoretically can help as well. So we think even with the most basic composite pulses, those could significantly improve the performance. But with that being said, which improve or which require only a modest boost in pulse area by a factor of 2 or 3. But with that being said, we've been using some commercial software made by a company called Q-Control in Australia to do some simulations of actual optimal quantum control protocols where, and of course, as you're right to point out, you can gain your fidelity and robustness by going to larger and larger pulse areas, which is indeed something that's bared out in the simulations. And one feature that's actually good about the strontium clock transition, as opposed to, say, previous work with rubidium atoms, is because the spontaneous emission rate is much lower, we actually have more, we're less constrained by spontaneous emission time, because for rubidium atoms, you'd be really worried about increasing your pulse area by more than a factor of 2 or 3 before the extra time the light is on, and the spontaneous emission that increases due to that causes more atom loss than you're mitigating with the optimal control. But with strontium, since the spontaneous emission rate is so much less, we could potentially go to a much larger multiple of the pi pulse time in our optimal quantum control sequences. Of course, we do have to ensure, since our nominal pi pulse time is on the order of several hundred microseconds, we can't go doing a 100 millisecond optimal control pulse, because then we won't have time to do enough LMT enhancement pulses. But there is, I think, room to use larger multiples of the pi pulse time for optimal control than one might have in rubidium due to this reduced spontaneous emission rate, while still squeezing in a fair number of pulses.
I guess following up on that, sorry. So in rubidium, what prevented you from just going to larger detunings effectively to match the line width of the strontium transition?
Right. What in rubidium, what practically prevented that was just limited laser power, because as you go to larger and larger detunings, your effective 2-photon Rabi frequency then is dramatically reduced. And so it turns out in order to get the spontaneous emission rate as low as in the strontium single photon transition, while still maintaining a comparable Rabi frequency to what we're getting for the strontium clock transition, we need really a quite enormous amount of laser power that we didn't have available.
Yeah. Yeah, I think that's right. I mean, if I remember correctly, the laser powers were being pushed to hundreds of watts anyway.
Yeah, I think in our in the initial version, we had sort of on the order of tens of watts, and then in their most recent laser system in the Kasevich group, since that was sort of beginning when I was there and has come online in recent years, it is on the order of 100 watts now. That's correct.
Okay. Okay, that's as I say, a fascinating talk, and I'm sure we could discuss it for a long time. But I mean, I think we should probably, I'm sure the Zoom etiquette, bring the sort of formal part to an end. And thank you very much for spending the time to explain all this to us. But you know, I think we also be opportunity maybe for people to stay in the Zoom room and discuss a bit more informally if people have got other questions, and if Daniel wants to finish off his question.
Absolutely.
So thank you again very much for doing that.
Yeah, thank you again for the invitation.
Okay. So I still see we've got plenty of people on the line. So are there any other talks people want to say, ask things that they were too diffident to say when there were a lot of people there? Did Daniel want to? Sorry, I stopped you in the middle of talking with Daniel, but
no, that's fine. Yeah, I could ramble on about cameras and detection forever. So it's good. I probably could have gone on for a very long time. So it's good.
Well, I was conscious that after 1 hour, you know,
exactly,
there's a significant number of people go on to the next meeting. So
yeah, I appreciate very much you giving an answer there. I'm sure that we're likely to have. I appreciate that you have an hour here, and we're likely to have these discussions in more detail in the future. But yeah, my point was just, of course, we're starting to think now about the you know, the design of this imaging system, and we had a very illuminating talk only yesterday, actually, with Jason Hogan from Stanford.
Oh, excellent.
Yeah, and so we are just now beginning to understand essentially what are the main parameters of importance for you guys, you know, to do the science that you want to do with the images that we take. And so yeah, this was the general idea of my, just in a general sense, as you answered very well. You know, if for example you have opportunity to trade off a little bit of QE for better depth of field, or these kind of considerations, yeah, what your feeling is in terms of what you would like to see, you know.
Yeah, right. In terms of the, so yeah, in terms of the electronic noise, just as low as we can get it, as I mentioned earlier, that's,
yeah, which is why we,
favorable. But in terms of like things like depth of field, what I think would be a favorable set of parameters is if for our atom cloud size, which I'd anticipate being on the order of several millimeters, if we can maintain good enough depth of field to be able to resolve spatial features on the order of 100 microns over that full size of the atom cloud, I'm thinking that would be ideal if we can